We're going to go over the properties of radicals. We have the properties listed here. So the little n is your index. So we're going to let n equal an integer greater than or equal to 2. And a and b are going to be real numbers. The inverse property says that if the number inside the radical, the exponent, if that exponent equals the little number on the outside, which is the index, then we can cancel that out and just get a. So it cancels out and you get a if the index is odd, but if n is even, you actually get the absolute value of a instead of just a. So that's the difference between these. In either case, the radical does cancel out, but if it's odd, you just get a. If it's even, you get the absolute value of a. The next property is a product property. So I can go either direction with this. I can either start with a combined radical, and I can break it apart and get 2 radicals or 3, depending on how many you have. It could be more than just 2 that you see here. It could be A, B, and C, and A, B, and C here. Or if you could have the separated ones, and you can put those together, multiply them together to get 1 radical. The quotient property is very similar, except that you have division going on instead. You might have a case where you've got 1 big radical, and you can separate it by taking the nth root of the top and the nth root of the bottom separately, or you might have these separate and you want to take them back into 1 radical. So you can go either direction with these. So now let's apply these properties with a couple examples. This first one would be an example of the inverse property. We notice that the power on the inside matches the index on the outside. Therefore, these cancel out. Now, since the 9 is odd, that means we're just going to get 10. We don't need the absolute value there in that case. So the 9th root of 10 to the 9th, essentially these are going to cancel, and you're just going to get 10 as the answer there, and that would be it for that one. For the next one, we're going to apply the product property because we have a combined radical, and I want to separate that into 2 different radicals. I'm going to separate it by doing one with the number, with 243, and since the other one is a variable, that's why I'm kind of separating it and doing that one on its own. So I have the 5th root of a number, and then I have the 5th root of something with an x in it. Now that I want to break down this 243, if you don't know what that is off the top of your head, that's okay. You can just go ahead and do a factor tree on this. So 243, since it ends in the 3, you can try dividing by 3 first. That's a good number to try. And if you do, divided by 3, you'll get 81. And then 81, that goes into 9 times 9, and then each of the 9s goes into 3 and 3. So this factor tree I'm doing here, what you're actually doing is you're writing this as a bunch of primes. A prime number would be one where you can't really divide it anymore by anything else except itself and a 1. So 3 would be as far down as you could go on that. There's 1, 2, 3, 4, 5 3s, and that means that you can write 243 as 3 to the 5th power. And then we still have the 5th root here. This one, 5th root of x to the 5th. All right, so this one, the 5 inside and the radical, that's going to cancel, and you're just going to get 3. And then this one, the 5 inside and the radical outside will cancel, and you'll get a x for that. So therefore, that tells us that the 5th root of 243 x to the 5th, that's going to turn into 3x. So that would be your answer on that one. Let's do a couple more examples. All right, so this one, it may look like we're going to apply the quotient property here, but if we do, what's going to happen is we have the cube. This is a 3 here, so that's a cube root of 135 x cubed, and we have the cube root of 5. Well, the cube root of 5 can't do anything with that, and the cube root of 135, you're not going to be able to do anything with that either. So instead, you might want to try and divide these numbers first to see what we get as a result. So if we do 135 divided by 5, then you're going to get 27. So 27 is something that we can write as a power of 3 because 27 goes into 3 times 9, and then that would be 3 times 3. So therefore, what I could do is this is going to turn, first I'll write it as the 27 like that. But then we know that 27 can be written as 3 cubed, 3 raised to the third power. And then x cubed we have there as well. Then we can use the product property to separate this. So we're going to do the cube root of 3 cubed times the cube root of x cubed. Well, this part here, the 3 and the root cancel and you get a 3. And then this one, the 3 and the cube root cancel and you get x. So therefore, the cube root of 135 x cubed over 5, that's just going to equal 3x. So 3x would be your answer on that one. Now, this one's a little bit different because we have x to the 12th power. So now, like the other examples we did, the power in the x equaled the same power as the one on the outside. Now, if that doesn't happen, then what you want to do is you want to break up the x to the 12th into groups of 6. Now, in order to be able to do this, you have to know a property of exponents. And so x to the 12th is the same thing as x to the 6th times x to the 6th. So if you multiply two x's together that have the basically two things that have the same base, you're going to add the exponents together. So x to the 6th times x to the 6th equals x to the 12th. Now, of course, I can break this down other ways. I could have done like a 2 and a 10 or a 4 and an 8. But specifically, I want the powers of 6 so that it matches the little index that I have on the outside. Okay, so I'm going to do the 6th root of 64, and then I'm going to do times x to the 6th, and then times x to the 6th. So that's the first step I'll do in breaking this down. Now, the 64, we want to break that down further. So I'll do another little factor tree with that. 64 is 8 times 8. This is a 2 and a 4, and this is a 2 and a 4. And then the 4 can be broken down into 2s as well. So you have 2 multiplied by itself 1, 2, 3, 4, 5, 6 different times, which means that I can write this as 2 to the 6th power inside. So 2 to the 6th. And then at the same time, I'm also going to break all these radicals up. I'm going to use that product property again to break all this up. Okay, so I broke it up and did these two separately, and then I broke up the 64 and turned it into 2 to the 6th. Now I can use the inverse property on these. So all these radicals are just going to cancel. I get 2 and I get times. Now remember, when you have an even power, it's not going to be x. It's going to be the absolute value of x. So we actually have this. We have 2 of these. Now that can also be written as the absolute value of x squared. Now, what we know about something, when we square something, we're always going to get a positive number no matter what. So it's kind of redundant to have an absolute value and a square because it's basically making something positive twice. So we don't need the absolute value in here. We can actually just write it as 2x squared, and that would be the most simplified form. That would be your answer.